So let us start, because now it's 6:30 Rome time.
Okay, cool. Thank you for the introduction.
Okay, thank you.
So my name's Sebastian. I'm a PhD student at Macquarie University and the newly established Sydney Quantum Academy. Now, before I get started, I would like to say a quick thank you to the organizers and session chairs for the efforts in managing this year's Master Grossman meeting and moving things online. I know it's probably not the way most of us had hoped things would go down, but it's still a lot better than not having a meeting at all, I believe, so thank you. And as you can probably tell from the title of my talk, I will be reporting on some new results pertaining to the treatment of black holes in the semi-classical framework. And this is done in collaboration with Rob Munn from the University of Waterloo, Valentina Bacchetti from RMIT University in Melbourne, and my supervisor, Daniel Turner from Macquarie University in Sydney. Now, since this session is on theoretical and observational studies of astrophysical black holes, I want to start off by showcasing some examples of observations, because especially in the last couple of years, we've seen a plethora of evidence for the existence of astrophysical black holes. So some 5 years ago, the detection of gravitational waves that were emitted in a merger of two black holes was announced by the LIGO and Virgo collaborations. So this was almost exactly 100 years after Einstein initially published his theory of general relativity. And of course, many similar events have been detected since. And in fact, you can actually go to the LIGO website where they keep a running tally of all the latest gravitational events that have been detected. Then many of you will probably remember this photo here from 2 years ago, which was published by the Event Horizon Telescope collaboration. And it's an image that shows a light ring surrounding what is supposedly a black hole. And actually, this study has been updated in October last year. And what they've done here is they've used their observations to place very stringent constraints on how significant deviations can be from general relativity while still being compatible with the observational data that they've recorded. And you can do this because the size of this shadow region tells you something about how strong the gravitational interaction is, or it gives you an estimate or a bound, if you will, on how strong the gravitational interaction is. And then, of course, last year's Nobel Prize in Physics was awarded to black holes, to Roger Penrose for his theoretical work on black holes, most notably the singularity theorem, and to Reinhard Genzel and Andrea Ghez for the confirmation of the existence of a supermassive compact object in the center of our Milky Way. And this was done, as you can see by the animation on the right-hand side, by just monitoring the motion of stellar trajectories in the vicinity of the galactic center. And at this point, I want to add here that the true physical nature of astrophysical black holes is still heavily debated. So it's not entirely clear what they are, and it's not entirely clear what it actually is that we're seeing. And this becomes apparent in many ways. For starters, you may have noticed that in the official announcement for the Nobel Prize, the Swedish Royal Academy of Sciences has no problem calling it a black hole when it's in reference to the theoretical work of Roger Penrose. But when it comes to observations of astrophysical black holes, they conveniently switch the language and refer to it as a supermassive compact object, which can be many things, really. And the two most popular models to describe astrophysical black holes are horizonless ultra-compact objects, and the other popular class is that they're genuine physical black holes with some sort of horizon. And of course, there are many sub-classifications that you can make in both of these classes, but for the purposes of my talk, I will just stick to these two big main classes, horizonless objects and those physical black holes that have some sort of horizon. And a bit later in my talk, I will actually present some semi-classical arguments that strongly favor one of the two models over the other. But before I do that, I want to briefly discuss the formalism of our approach. So in classical GR and related research areas, people often use the notion of the event horizon, which is a global and therefore observer-independent notion of the boundary of a black hole. However, it's very important to understand that an event horizon, even if it's a useful mathematical tool, is not physically observable. And because of this, event horizons are not useful for all practical purposes. On the other hand, there are notions of black hole horizons that are useful even for practical purposes. And the one that is most convenient for us is the notion of an apparent horizon. And unlike an event horizon, this is something that is a well-defined quasi-local observable. And what this means is that we can make a measurement in a finite size region of space and within a finite time interval to determine whether or not an apparent horizon exists. And because of that, this is actually the starting point of our work. And it's actually our only assumption that a regular apparent horizon forms in finite time of a distant observer, usually referred to as Bob. And what we mean here by regularity is simply that the two curvature scalars that you can construct from the energy momentum tensor components are finite at the horizon. So these two scalars can take on arbitrarily large values, but they cannot become infinite at the apparent horizon. And starting from just the single assumption, we try to investigate what are the consequences for the geometry near the horizon, what are the implications for black hole formation, what are the implications for black hole evaporation, and so on and so forth. And I've actually compiled a list of references here that summarize our results over the last 3 years. So if this topic is of interest to you, then you can take a screenshot and read up on the details later. The talk today will mainly focus on the results that are contained in this latest PhysRevD article in volume 103 here. And just for the sake of completeness, I also want to mention the two other popular gravitational collapse scenarios. So the first one here is the one that we're working in, where an apparent horizon does form in finite time of a distant observer. The second popular possibility is what's called continued or ongoing gravitational collapse. And this is where the notion of a horizon is merely an asymptotic or T to infinity concept. And what people usually do here is that they define a closeness parameter. For example, the coordinate distance between the actual physical radius and the horizon radius, and then they monitor this parameter until it reaches some prescribed value, usually a very small value, in some finite time of a distant observer. And the third option is that due to evaporation or maybe some other reason, a transient object is formed where the minimal value of this closeness parameter is reached at some finite time of a distant observer, but then it can increase after. Now, it's important to note here that the first scenario, the one that we're working, is actually the only one that allows for the possibility of information loss. So what this means is that if you believe the information loss paradox is a real problem, then you automatically also subscribe to believing that this first scenario is the correct description of gravitational collapse. Because in the other two scenarios, you cannot have information loss. It's not possible, not even in principle. Simply because you don't have a suitably horizon to trap information to begin with. And I would also like to point out already now that it has been shown that this first scenario does require the violation of the null energy condition. And I will get back to this later in my talk. Now we're working in the framework of semiclassical gravity, so I want to briefly explain what this means. The great insight of Albert Einstein was that the geometry of spacetime is the manifestation of the gravitational field. And in his famous paper from 1916, he put this notion in a precise mathematical form through the formulation of what we now know as the Einstein field equations. So these are equations that relate the geometry of space to a distribution of energy and matter. And the reason we can treat energy and matter on the same footing here is Einstein's other famous formula, which tells us that one can be transformed into the other. Now, in semiclassical gravity, what we want to do is we want to take into account quantum effects, at least on the right-hand side of the field equations. We don't know how to do it on the left-hand side. If we did, then we already would have a fully developed theory of quantum gravity, but we don't. But on the right-hand side of the equations, you can take quantum effects into account. And you can do this by considering the expectation value of the energy momentum tensor. And quantum effects play a pivotal role in processes, in dynamic processes, such as black hole formation and evaporation. And usually what people do here is they specify a quantum state and then they work with the renormalized energy and momentum tensor. But here in our work, we do not assume any specific matter content or any specific quantum state. Our goal is to simply investigate the generic scenario and see what statements can be made without making any additional assumptions. We also work in spherical symmetry, and a generic spherically symmetric geometry is described by the infinitesimal line element that I've written down here, where this function f is defined as 1 minus c over r. And this function c you're probably familiar with. It's the Misner-Sharp mass. And this is a very convenient definition of the mass because it's invariant, so it will be the same across different coordinate systems. And speaking of coordinate systems, the second metric function h essentially can be thought of as an integrating factor in coordinate transformations. For example, the generic transformation that I've given here between TR and VR coordinates. But now, what does spherical symmetry mean when we look back to the Einstein equations. Well, another way to specify the geometry is to just write down the metric tensor. And by looking at the line element, you can see that all the terms appear in the squares of the coordinates. So this metric tensor has a diagonal form. Now, the important thing to point out here is that in spherical symmetry, all equations that contain angular components are actually not very interesting because they don't give us any useful information that we can use. So if we want to get the field equations in spherical symmetry, it suffices to look at the TR block of the field equations, and the TR and RT components of the metric tensor are actually 0, but the Ricci tensor and the energy momentum tensor components are not necessarily 0. However, it is possible to use the symmetry properties. So RTR is the same as RRT, and the same for the energy momentum tensor. So you can actually write those two equations, TR and RT, in a single equation. And so in total, you will end up with 3 equations for the TT, TR, and RR components. And as you can see, these are just differential equations of the 2 metric functions. Now, the tau functions that you see on the right-hand side here are just the energy momentum tensor components multiplied by some factor of e to the power of minus h. And the only reason for this definition is that it allows you to cancel some exponentials in the equations. So it makes it easier to deal with mathematically. And that's the only reason why we've defined these tau functions that you can see here on the right-hand side. Now, I want to briefly recap 2 important results that are going to be relevant for what follows. The first one I've already alluded to in my introduction, namely that real-valued solutions of the Einstein equations that correspond to physical black holes necessarily require that the null energy condition is violated. And this is actually a known result that was first derived by Hawking and Ellis. However, in their derivation, they made some assumptions about the asymptotic nature of space-time. And here we make no assumptions about the asymptotic nature of space-time and get the same result. However, we do explicitly use spherical symmetry, which Hawking and Ellis have not done. So these are 2 results that really complement each other quite nicely and end up with the same result. The second important result for today's talk is that there are actually only 2 distinct classes of solutions corresponding to physical black holes. And with respect to the regularity requirement that we've defined for the curvature scalars, the 2 classes of solutions actually correspond to 2 values that this parameter k can take on. And so this parameter k sets the scaling behavior of the components of the energy momentum tensor. And it turns out there are only 2 values that are consistent and do not lead to contradictions. And those 2 values are k equal to 0 or k equal to 1. And so we usually refer to the 2 classes of solutions as k equal to 0 or k equals 1 solutions. Now, the first result from our latest paper is the derivation of an explicit expression for the transformation between TR and VR coordinates near the horizon. And the reason VR coordinates are extremely useful is that they provide a natural description of dynamic black holes that is non-singular. So for evaporating black holes, for example, VR coordinates are the most convenient set of coordinates that you can use. Now, how do we obtain an explicit expression for this transformation? I had already written the generic transformation earlier when we talked about the metric function h playing the role of an integrating factor. So we can certainly use this relation. And we get a second relation by considering ingoing null geodesics near the apparent horizon. And then simply by combining those 2 relations, we end up with an explicit transformation between TR and VR coordinates that is valid in the vicinity of the horizon of an evaporating black hole. And speaking of coordinate transformations, we actually also know of some relations that relate energy momentum tensor components in VR and TR coordinates. And those are the 3 that I've written down here. Those are the 3 relevant ones in spherical symmetry, I should say. And if we consider the K1 class of solutions, then these tau functions will scale as f to the power of k, but k is just 1. So they just scale with f. If you write it down explicitly, it looks like this, where E, P, and phi physically just correspond to the energy density, the pressure, and the flux at the apparent horizon. And what's written below here is just a generic expression for the Misner sharp mass in VR coordinates. And what we found, it turns out that the first relation between the energy momentum tensor components can actually only be satisfied if the linear coefficient in the Misner sharp mass is equal to 1. And what this tells you is that if you define a function delta v, which is just this Misner sharp mass minus the aerial coordinate, it'll change sign at the apparent horizon. And this tells you that the Misner sharp mass in VR coordinates cannot have a square term. And now the important thing to remember is the Misner-Sharp mass is invariant, so it has to be the same in all coordinate systems. So we can compare this expression with the expression in TR coordinates, and then we get the expression that I've written down at the bottom here. And you can see that there's actually only one way to make this y squared term disappear, and it's for the specific value of the energy density that is 1 over 8 pi RT squared. And it turns out this is actually the extreme value of the energy density. So sometimes we also refer to the K1 solution as the extreme K1 solution. And this is our unique solution. So this is the only consistent solution for this K1 class. Now, what does this imply for the formation of black holes? Running a little low on time, so I will just skip to the conclusion here. And what we found essentially is that in order for a black hole to form, you need to satisfy this condition here. Omega 1 minus 1 is 0. So this only leaves one solution, which is omega 1. And this is, of course, the K1 solution that we found on the previous slide. So what this tells us that at the instant of its formation, a physical black hole is described by this K1 solution that is necessarily extreme. And we found that then immediately after, the behavior actually switches to the the K0 solution. And just as a side note, we were also able to provide some arguments that actually show that these two classes of solutions are the only possible perturbative solutions in various modified theories of gravity. I'm also going to skip the derivation here. The question we set out to answer here is, well, is there a sensible way to generalize the concept of surface gravity for dynamic physical black holes? And what we found is that the Peeling surface gravity actually diverges. So the answer is, for dynamic physical black holes, there is no sensible generalization of this very important concept of surface gravity. And this is actually one of the arguments why the semi-classical analysis favors horizonless ultra-compact objects, the model of horizonless ultra-compact objects as astrophysical black holes. But you can make an even stronger argument that I haven't mentioned yet, simply by comparing the required energy and timescales with the known standard results. And if you do this, we've done the calculation in our paper. And for example, for a solar mass black hole, we have found that the formation time is something like 10 to the power of 64 years, which is about 4.5 times the age of our entire universe. So you will find it simply does not work out. It doesn't match. And this has very important implications, for example, for the informationless problem. So just to briefly recap, the problem here is Stephen Hawking has shown that black holes can evaporate. And moreover, he has shown that the radiation that is emitted in this process is completely thermal. So it carries no information about the black hole other than the mass and the temperature. But from the mass and the temperature alone, you cannot deduce what fell into the black hole. And this is a problem because time evolution in the quantum theory is unitary. So information has to be preserved. So the conundrum here is, well, if the black hole evaporates completely, where did the information go? But of course, this problem or this paradox hinges on the existence of a horizon. So if there is no horizon, there is no paradox. So our semi-classical analysis actually resolves this paradox. Now, there's one more option that I want to mention. You can, of course, say, well, semi-classical gravity is wrong, and there's some new physics that gives you a horizon. It's not what we usually do in physics, because when we assume new physics, we usually do it to get rid of problems. But here, you're assuming new physics and you're sort of creating new problems, because obviously if you have that horizon, then the horizon, the informationless problem is still a problem, whereas with just semi-classical gravity, it is not. But nonetheless, you can do this and you can take care of new physics with modified theories of gravity. And we have actually looked at this scenario in a separate paper that I've referenced here. And since I'm running low on time, I will just mention here, if you're interested in this, I actually will be giving a second talk in about 3.5 hours about this topic, and you can tune in there. And since my 20 minutes are up, I will just leave you with the summary and outlook slide and open the virtual floor for questions. Thank you.
Thank you very much. Thank you again for your perfect timing. We have time for a couple of questions. If there are questions, please raise your hand, and I will give you opportunity to ask question. Please. Any question? Sumanta, please ask.
Yeah. Hi, Sebastian. It's a very nice talk. So my question is that you mentioned in presence of apparent horizon, there is no information loss paradox. Does that mean that if we have a quantum field theory on the black hole spacetime that you have, do we have a non-thermal radiation at infinity, and can you quantify that?
I don't know. So to be honest, I don't know the answer to your last question about non-thermal radiation. But the thing with the apparent horizon is that it doesn't, you can have an apparent horizon, but not have an event horizon. It's possible, but not required. Our analysis doesn't make any assumptions about the formation of the event horizon, just because an event horizon is unobservable. So whether or not it exists for practical purposes doesn't matter. The only thing that you can prove in principle is the existence of an apparent horizon. And it turns out, even with just the assumption of the apparent horizon, you already run into problems if you do semi-classical gravity, because as I've mentioned, the results strongly favor the horizonless model. I mean, you can't, I mean, the numbers you get for physical black holes are just incompatible with the observational data that we know if you compare the required energy and timescales. So you already run into problems here just with apparent horizons.
Okay, and just one more question. So if
Yes,
you
yes,
have
go
this
ahead.
type of, yeah, you have this type of solutions like horizonless geometry. Have you tried to look at their implications in certain observational sector? For example, the quasi-normal modes. Do they show some abnormalities? Can you have some comment on that?
Yes, we actually are looking at quasi-normal modes. We don't have a paper about this yet, so I cannot give any definite results about this yet, unfortunately. But we are looking into it, and it's a very interesting avenue for future research, I believe.
Oh, thank you very much.
Other
Thank you.
questions? Other questions? If not, let us thank speaker again for excellent talk and excellent presentation, for excellent timing. Thank you. Thank you very much.
Thank you all.
And
Bye.
thank you. And next speaker is Sushant Ghosh. I apologize for wrong pronunciation of your name. Okay, good. Full screen mode, please. Okay, good. Go ahead. Thank you.
Thank you, Alex. Thank you, organizer, for giving me chance to speak on our work on Hairy-Kerr black hole and observation of Event Horizon Telescope. So the black hole is in the news for the various reasons we all know. So there are numerical astronomical questions that are likely to be addressed with the Event Horizon Telescope observation, and we can also expect that new exciting questions can be asked. However, it will be interesting to inquire whether Event Horizon Telescope results can shed light on the important question of dark matter. Here we consider the Hairy-Kerr black hole and see what are the constraints from the Event Horizon Telescope observation of M87 black hole. Okay. It's not going on. It's not going. Yeah. So the starting point is no hair conjecture. We know that this is the conjecture which is coined by Wheeler, and which says that stationary isolated black hole in DR are uniquely determined by the three parameters: mass m, angular momentum j, and the electric charge q. All other parameters are likely to be here. Since the astrophysical black hole in the universe, the charge is thought to be negligible, so astrophysical black holes are described by the Kerr black hole. Now, heavy black holes are termed as stationary black hole solution with new global charges, which are not associated with Gauss law. So we are considering a metric which was proposed by Czech people, by contrast, Valle and Casido, which is based on a gravitational decoupling approach. It's a very simple approach to generate rotating black hole, and the only requirement is that strong energy condition or the dominating energy condition is to be satisfied. Now, this is the addition. This is the simple metric of the Hairy curve black hole. It looks like exactly like curve black hole, but there is an additional term here. Additional term which is coupled. Alpha is the coupling parameter, and this term may arise because of the surrounding dark matter. That is what they said, and also it could be a solution of the appropriately modified gravity, which they have not investigated. And so this is a modification of curved black hole, and the curved black hole is encompassed as a special case in this. So we are interested in using this and put constraint from the event horizon telescope. Now, first thing is how the parameters are modified. Now, if you consider the parameter, because there are two new there are one parameter alpha 0 and alpha and L0. They can be in fact connected to each other, but I have plotted L0 A space of A and L0, in which it shows the upper side is no black hole solution or a naked singularity, and black hole solution is the lower side. So this is the parameter allowed for the black hole, and this is not the forbidden region for the black hole. And this region can changes with the variable alpha as well as variable L0. So now investigating the normal event horizon, Cauchy horizon, static limit surface, the standard definition is followed. And we know that the region between the event horizon and the static limit surface is called ergo region. So I won't waste our time on that. So this is the plot of Hairy curve black hole horizons. Now it is obviously dependent on alpha, and the black line, the lower black line in all the figures correspond to the curve case, which is the limiting case. So we can see that the horizon radius decreases in the Hairy curve black hole. As you increase the parameter alpha or parameter L, in the horizon radius decreases, and we can find a extremum parameter of L0 or even alpha 0 for when the value of alpha is less than this extremum value, we have black hole, otherwise there is no black hole. So that is shown in these figures, and also we have shown the ergo region. So ergo, pardon? Hello? Can this Sarah, please mute your voice. So ergo region is dependent on alpha as well as L.
تایمتیبل روی عنوان سخنرانی کلیک می‌کنیم.
So I will ask all people except speaker, mute yourself.
Thank you. Please don't mute my mic. My microphone was also muted. So this has consequence on the Penrose process, because the ergo region gets expanded because of the Hairy curve black hole. So I won't go into detail of that. That is right. So yeah. So let's go back. Let us talk to the main topic, the shadow of black hole. A black hole embedded in normally optical thin emission region will produce an observable signature, namely a shadow cast by a black hole, which is strongly gravitational lensed image. The concept of black hole shadow is in the literature for very long, but imaging was possible. Thought of imaging was possible only when the paper by Filicki came in 2000. The intrinsic shape we'll see of the black hole, the shadow depends on the geometry of the space-time, the boundary which separates the trap from those from escape, is called the is called the photon sphere. So that is right. So we are interested in the motion of the particle. The motion of the geodesic photon around the black hole is necessary to study the shadow formation. And for this purpose, we consider Hamilton-Jacobi equation. Since as in the Kerr case, the matrix doesn't depend on t and phi, so it admits two Killing vector, and we can write the Hamilton-Jacobi in the first differential form. Now there are three apart from normal, there is a Carter constant K. Now the Carter constant K allow us to completely integrate the geodesic equation. So this is what is done, and then the photon sphere is an unstable circular orbit that can either co-rotate with the black hole or counter-rotate. Now the co-rotating orbits are within the region m to 3m, whereas counter-rotating are between 3m to 4m, and they are solution of the impact parameter eta c is equal to 0. So it is the co-rotating orbit's radius is less than counter-rotating, and this is because of the length thrilling effect. And this is shown in this schematic diagram. And for the Kerr case, I put exact solution for this, the co-rotating and counter-rotating. This will be used for the shadow purpose, right? So to proceed further with this equation, we introduce the impact parameters eta and zeta. They will reduce the number of variables, and they are useful for solving the. Pardon? Mathematically, this corresponds to the local maximum of radial effective potential outside the horizon, at which photons follow the unstable orbit at the radius rp. So we can have this r dash, and if you solve this, then we can obtain the critical value of the impact parameter, and this will help us to plot the shadow. Right now, if you make a stereographic projection of black hole shadow in the observer image plane, then they are governed by the celestial coordinates, which are defined by this. And in the case of Kerr black hole, it can be hairy Kerr black hole as well as Kerr black hole. This can be evaluated exactly. And when you are in the equatorial plane, then it becomes very simple form, which is here, equatorial plane. We have written x and y in terms of this hairy Kerr black hole mass, where m of r is mass, m is the mass of the Kerr black hole, and we have additional term because of the hairy, right? So this is the plot. Now first is the plot for the non-rotating hairy Kerr black case, and the outside one is the Schwarzschild. It will become a Schwarzschild like hairy Kerr black hole. So we can see that this the radius of the shadow decreases with the alpha as well as L0. And on the right hand side, when you take alpha to be 0, you get the Kerr black hole shadow. And this is the for rotating case, and with the various parameters, with the varying alpha and the varying L0. We can have varying L0 as well as alpha. So in the plots for a given alpha and for a given rotation parameter, we are varying alpha, and the plots are there. The outermost orbit, is corresponding to the Kerr black hole, and therefore the Kerr black hole has bigger shadow compared to the hairy Kerr black hole, right? Now let us use the application of finding using shadow to find parameter associated with the Kerr black hole or hairy Kerr black hole. Now the original first method, and there are many methods available in the literature, was given by Hioki method. Hioki method proposed the first, and that method was based on the radius observable RS and the delta S distortion, right? But in that case, you need to have a proper symmetry for the shadow shape. So we have proposed a new method based and that Hioki method doesn't work for a haphazard black hole shadow, and that is possible because of the noisy data. So we have proposed a new observable A and D. This is with my scholar Rahul, where A is the area of the shadow and D is the distortion, right? And mathematically, distortion can be maximum 3/2 for the Kerr case and 1 for the Schwarzschild case. So what we do, we plot them in the contour plot. We make a contour plot of this A and D, right? In the plane of A and L0. Capital A is the area, D is the distortion, and A in the L0 plane, rotation, and the L0 is the hairy Kerr black hole. Right, right. So this, if you take the intersection will determine uniquely the parameter associated with the black hole shadow, right? So if you see in the table this A and D, for given A and D, you can easily find A and L0. A is the rotation parameter, L0 is the hairy Kerr parameter. So for a given alpha, you can find various parameter associated with the black hole shadow. So that was the reason. Now I want to talk about some results of the event horizon telescope. Now we know that the event horizon telescope gave the result. Sorry, right? Okay, because I'm running short, right? So it uses VLBI technique, and it is a global array of the radio telescope, and it gave the result in the 2019, and some of the result is like this, that they propose the mass, right? So this mass and this the estimated mass is given here. So original observation was done in 2017, and after 2 years, there were 6 papers in the FJ latest produced. The Sagittarius A star was also observed, but its result was not released because of some reason, right? The asymmetric ring, which is shown on the left side, asymmetric result is the combination of strong gravitational lensing and relativistic beaming, right? And the north-south symmetry ring is controlled by the rotation of the black hole. So this, and the mass of the black hole is estimated at 6.5, which is slightly more than the earlier predicted result, and the crescent diameter is the 42 plus minus 3 micro arc second, and gravitational radius is this. So the information about the orientation of the black hole spin was also said, but no value of the rotation parameter was given, right? The mass value, as I said, is somewhat higher than the previous said value. The other objects, the like naked singularity, cast very lower shadow, so they were not considered. Now what we want to do, we want to use this, but boson star or other like Grava star were not completely ruled out. So what we want to do, we want to use hairy Kerr black hole to constrain this. Our main is this circularity deviation. The circularity deviation was less than 10%. So I want to use this constraint for the hairy Kerr black hole. And in the case of hairy curve black hole, it is satisfied. You can see it is a density plot, and you have to have the circularity deviation less than 10%. So this is satisfied for the entire parameter space, of the hairy curve black hole. The white region is forbidden region. Region is the forbidden region. So that is one observable. The second is the angular diameter. This is very important. The mass of the black hole we are using the proposed by the proposed by the Event Horizon Telescope, 6.5 into 10 to the power minus. Distance is same, 16.8 parsec, and then we calculate the angular diameter. Now this black hole line, the black line is the result given by the Event Horizon Telescope, because Event Horizon Telescope estimated the angular diameter of 42 plus minus 3 macro arc second. Now, if we take 1 sigma level, so this is plotted at 39. So the region inside the black line is in agreement with the Event Horizon Telescope, whereas outside the region is not. So hairy curve black hole is consistent with the Event Horizon Telescope in the finite parameter space. Now, last is about the axis symmetry. Now, this is another way. So another way of circularity deviation. So this is satisfied. In the entire parameter space. How much time now? Huh? Okay. So this is also satisfied in the entire parameter space. So we have following conclusion. The circularity deviation should be less than 10%. Is satisfies for the entire L0 A parameter space at both 90 degree as well as 17 degree. The angular diameter is satisfied within 1 sigma region again for the finite parameter space. It is not true for the entire parameter. But for 30, if you take 17 degree in the figure, it is smaller area, smaller parameter space in the 17 degree. The upper half is the 90 degree, the lower half is 17 degree. So it has the lower parameter space. Right. Now, axis ratio is satisfied for the entire parameter space for both 90 degree and the 17 degree. The 17 degree was used by the Event Horizon Telescope. We have used both 90 degree. 90 degree is easier for the calculation purpose. Right. So we can say that shadow M87 Event Horizon Telescope observation of M87 do not entirely rule out hairy curve black hole. And the departure produced by the hairy curve black hole, even if there is a departure, it is order of the micro arc second. So this departure cannot be resolved by the present Event Horizon Telescope, and one has to wait for the future. Now, future observation of M87 new generation Event Horizon Telescope can pin down exact constraint, may pin down the exact constraint, and may provide the signature for dark matter, because the hairy curve black hole in the question is likely to be because of the surrounding dark matter, maybe because of the surrounding dark matter, or maybe because of the modified theory. So we can say that in a way the modified theory gravity is not exactly ruled out. Event Horizon Telescope didn't say about the modified theory, but they didn't rule out it also. Lastly, our result in principle, if we take limit alpha 0 as I showed in the various figures, which goes to the curve black hole. And so from our result, black hole shadow of M80 horizon due to Event Horizon Telescope can serve as a tool for distinguish, because this solution can be also from the modified theory black hole, and can distinguish various models of the theories of gravity, eventually also shedding light on the nature of the supermassive black hole M87 and also dark matter. Now, if in the future event horizon telescope, there are likely to be have more telescope, and it is going to work on the shorter wavelength, 1.8 mm. At the moment, it is 1.3 mm. Now, lastly, Sagittarius A star. We are waiting for the Sagittarius A star. Sagittarius A star is tougher target, even though it is only 26,000 light years away, versus M87 of 55 million light years away. Sagittarius A star black hole harboring the mass of only 4.3 million sun, and therefore operate on much shorter time scale, and maybe that's why it is difficult to observe. So thank you so much.
Okay, thank you very much. Please prepare your question, but if there are no other questions, I would like to ask you a question first about slide number 14. About shadow for Kerr metric.
Yeah. Yeah, this is 40.
Yes, this one. You see, the maximal value in vertical direction is the same for all spin parameters. Do you know dependence? You see, the dependence of this maximal value for in vertical direction as a function of psi function in horizontal direction. Because if people could detect this shadow, in principle, directly you could evaluate spin. Do you understand?
Yeah.
Because very often people are using this shape of shadow, but you see there is a theorem. I will give you a hint. There is a theorem that maximum value is the same for equatorial direction, but position of corresponding x parameter is 2a.
Yeah. This is for equatorial plane.
But people are using this, but they don't know they did not point it out. That is very important, you know, because if you assume that you have Kerr metric and you could evaluate this shape, immediately you could evaluate spin. Right. It's something like a precise theorem, you know, exact theorem.
Okay.
It's just remark. And also about at the beginning you mentioned also, let us say, shadow and naked singularity. Do you have some cases of naked singularity when you have shadow or not?
Naked singularity we didn't consider, but I'm telling you, naked singularity has much smaller shadow. That's why the event horizon telescope result cannot be consistent with the naked singularity. So it has to be ruled out. But the Gravitational star and the boson star do have, because naked singularity also have photon sphere, but the shadow size is very, very small compared to the when you compare with the event horizon telescope. So it is entirely ruled out.
Okay, good. And also last question. Somehow there is at the beginning it was a hypothesis, Wheeler hypothesis about no hair theorem, but later people proved this theorem under some assumptions, of course, some conditions. In this case, in your case, probably you have to violate somehow some conditions of no hair theorem just to get some naked singularities. Could you comment about this?
See, this solution was proposed by this Ovale people. They say that this is a hairy black hole with the primary hair, but there is a controversy around that. It is exactly not. I mean, people objected the word of the hairy, but we have used the terminology of the originally paper given by this Czech people, Ovale and all. So I mean, anything, it has additional parameter alpha and L0, which they called as a L0 they called as a primary hair.
Sergio, do you want to ask question, short question or not?
Yes, in fact,
Please, short question and short answer, please.
Okay. Okay, so maybe first of all, thank you for a very interesting talk. And maybe I missed something in the beginning, but what is the physical meaning of this alpha parameter, and what kind of hair you talk about? A scalar one?
Pardon?
Please
what
repeat
is,
your question.
okay, what is the physical meaning of this alpha parameter?
Yeah.
I mean,
So
0 is the parameter of the hair, right? And alpha it is?
now alpha, see, I told in the beginning, alpha additional parameter came out. They gave a approach which is called gravitational decoupling, and they said that this alpha the additional term may be because of the surrounding matter around the black hole. They put is they should satisfy they didn't say exactly about the hair scalar field. They said it is because of the surrounding fluid, and the only condition they said that it satisfy the energy condition, strong energy condition. That was the only said. So it may not exactly correspond to hair scalar field, but that's what the original solution said. So we have utilized the solution.
Okay, thank you.
Thank you very much. So we have to go on. Thank you very much again for excellent talk. Thank you. And next speaker is Sumanta Chakraborty. Please stop sharing your screen, Sushant. Okay, good. Please go ahead. Fine, go ahead.
Okay. Thank you very much, Professor Zakharov, and thanks to the organizers for this opportunity. And good morning, good afternoon, good evening, and good night to all of you, depending on which places of the world you are in. So today I will talk about multiple moments of compact objects in asymptotically de Sitter spacetime. So we are familiar with multiple moments for asymptotically flat spacetime because that is used routinely in gravitational wave astronomy and also in various other theoretical aspects. However, we believe that this is the first instance where we have computed the multiple moments of asymptotically de Sitter spacetime explicitly. So I will try to lay out the foundation, the way we arrived at the multiple moments, and I will use a particular example. So this work has been carried out in collaboration with Jahanur Haq, Roberto Oliveri, and Sajol Mukherjee. All are at some university or research institutes at Prague. And I am from Kolkata in India. So this is a brief outline of my talk. I will first talk about a different way of computing multiple moments, namely the Noether charge formalism. Then I will discuss the de Sitter spacetime in harmonic gauge. I will explain what this gauge is and why it's important. Then I will talk about certain residual gauge transformation and the multiple symmetry vector field which is associated with it. So, okay. And then I will talk about perturbations of the de Sitter spacetime in cosmological coordinates. And finally, I will discuss multiple moments of Kerr de Sitter spacetime, which will be as an example of this scenario. So the two main references on which the talk would be based on are given below. So if you are interested, please go ahead and take a look. So let us talk about the multiple moments in asymptotically flat spacetime. So for that, there are three well-known formalisms at our hand. So first one is, of course, the Gerock-Hansen formalism, which was developed by Gerock and later on extended by Hansen. So this actually requires a stationary situation in the sense that it requires the existence of a time-like Killing vector field, which that leads to a twist potential, which of course can be generalized for the case of asymptotically de Sitter spacetime as well. But the problem comes at the next step, which requires finding out a three metric, which is orthogonal to this time-like Killing vector field. And that must be asymptotically flat for the Gerock-Hansen formalism to be applicable. The second formalism, which is due to Kip Thorne, that effectively requires expansion of metric coefficients as powers of 1 over r, and various multiple moments can be read out from various powers of 1 over r. But this again requires a particular coordinate system known as the ACMC coordinate system, which is asymptotically Cartesian and mass centered, and that again requires asymptotic flatness to start with. The last one, which we will concentrate in this work, is the Noether charge formalism, where one effectively tries to compute certain vector fields which preserve the harmonic gauge condition. And it turns out that if you compute the Noether charge associated with these vector fields, they are precisely the multiple moments of the corresponding spacetime. So in particular, just for reference, if you consider a Kerr black hole, then the mass and the spin moments of the Kerr black hole are written below. The capital M corresponds to the mass of the black hole and A corresponds to the rotation parameter. So you can see that only even mass moments are non-zero and only odd spin moments are non-zero. These are due to symmetry of the Kerr black hole above the equatorial plane. And we will try to see how this formula gets generalized for a Kerr de Sitter black hole in particular. Now let us talk about the flow chart that we'll take, namely the derivation of the multiple moment. So what we have to do, first we have to use the harmonic gauge condition, which effectively amounts to say that the metric must satisfy the condition that del mu of root minus g mu nu equal to 0. And for flat spacetime, this is obvious in Cartesian coordinate system. So that's why it is pretty easy to implement this condition for asymptotically flat cases. Next, we want to find out certain diffeomorphisms which will preserve this harmonic gauge. So effectively, if I make a coordinate transformation, which can be equivalently be transferred to a diffeomorphism by some vector field xi mu, then and we want this harmonic gauge condition to be preserved, we get a differential equation for this vector field xi mu. Thirdly, we also need to preserve certain asymptotic fall-off condition. In particular, this condition corresponds to the 0 mu component, that is the 0, 0 and the 0 I component, time, and time space component of the metric. They should reduce to the corresponding expressions for the flat metric with order 1 by r correction. So this condition should also be preserved by this vector field xi mu, which gives an additional set of conditions. These two sets of conditions, when combined together, can be solved in an exact manner and will lead you to a solution for this xi mu. So having derived the vector field, you can very easily compute the Noether charge, which is associated with the above vector field. However, you would need a background spacetime, and for that you take a linearized perturbation around that background. For example, whether it is Schwarzschild or Kerr, depending on that, and you see that it produces the correct multiple moments that you also obtain from the Gerock-Hansen or the Thorne formalism. So this was done in the paper by Geoffrey Compier, Robert Oliveri, and Ali Siraz in 2017. And this is the approach which we think is most adaptable to generalization to asymptotic de Sitter cases. And this is what we will follow. So before going to any further detail, let us briefly talk about various coordinate charts of de Sitter. What I have given on the right-hand side is the Penrose diagram of the de Sitter spacetime. There are effectively 3 coordinate patches which are important. So the global patch corresponds to the full square, which is described by the coordinates tau, chi, and theta phi. The cosmological patch is which I will be interested in. It is the triangle ABD, and this is described by the coordinates tr theta phi, where r theta phi can be transferred to Cartesian coordinates x, y, z, and t is the cosmological time. Or one can also use the conformal time eta, but for this purpose of this talk, I will just refer to the cosmological time wherever I will encounter de Sitter space. There can also be a static patch of de Sitter, which is this triangle AED, and that is described by the static coordinates capital T, capital R, and theta phi remains identical. There exists well-defined coordinate transformation between all of these patches. And as I said, I will concentrate on the cosmological patch. Let us now first do the first step in obtaining the multiple moments, that is finding out coordinates in which the de Sitter metric satisfies the harmonic gauge. Unfortunately, neither of the 3 coordinate system that I discussed, the harmonic gauge condition is satisfied. So we have to find out some new coordinates. So in particular, given the old coordinates x alpha, we can find out the new coordinate x bar mu. And it turns out that if I want this new coordinate system to satisfy the harmonic gauge condition, they should satisfy the equation, which is box for de Sitter acting on f mu equal to 0. So since the spatial part is almost identical to that of flat space-time, that's why we took x, y, and z to be identical to x bar, y bar, and z bar. So the Cartesian part doesn't change. While it's only the time coordinate which changes. So t bar goes to f of t. Then the function f of t can be solved by using the differential equation which arises out of the box equation, and the solution I have just written. So you can easily see that when h goes to 0, you can expand the exponential and you effectively get ft to be equal to t, which is what you expect, because in flat space-time, t, x, y, z are harmonic coordinates. So in particular, just for reference, I have given how the de Sitter metric looks like in the t bar x, y, z coordinate system and how it looks in the t, x, y, z coordinate system. Next step is the residual gauge transformation along with the asymptotic fall-off condition. So here also we want the asymptotic fall-off condition to be preserved and the residual gauge condition must be respected. So the asymptotic fall-off condition requires that the Lie derivative of the 0 mu component of the metric, de Sitter metric, should be 0. That means under the diffeomorphism, the 0 mu component should not change. It should retain the same structure. If you solve that equation, then you get the 0th component of the vector field and the ith component of the vector field, which I have expressed. And epsilon of x is an unknown scalar function of the spatial coordinates, and zeta I of x is also an unknown vector function of the spatial coordinates. So these two we have to determine. In addition, you see that h appears everywhere. So h is effectively the Hubble constant, which is related to the cosmological constant of the de Sitter space-time by the standard relation that h squared is lambda over 3. Again, when h goes to 0, one can explicitly check that the results matches with the results in Compier et al. Paper. But this is just one condition. It also must satisfy the residual gauge transformation. That means it must be invariant under, it must keep the harmonic gauge condition intact. Then you get additional conditions on this vector field xi, which gives equations for epsilon. So epsilon, for example, satisfies the Laplace's equation. The flat space grad square on epsilon should be 0. On the other hand, zeta also has a Laplacian, but there is an additional parameter which depends on the Hubble constant of the theory. So these two equations must be solved, and only then we can get the corresponding symmetry vector fields associated with de Sitter. This is the full structure of the multiple symmetry vector. As you can see, the time component just depends on epsilon of x, and the rest of it is the spatial part. So this can be decomposed into 3 nice sets. So there is a k epsilon, which corresponds to the mass multiple symmetry vector. There is an L epsilon, which corresponds to the spin multiple symmetry vector. And there is a P epsilon, which corresponds to the momentum multiple symmetry vector. The reason being, if I take h going to 0 limit, then k epsilon is precisely the vector field which will generate the mass multiple moments. L epsilon is precisely the vector field which will generate the spin multiple moments. And P epsilon will not give you any result. It will be identically 0 if you compute the corresponding moment of charge. So in the context of de Sitter, of course, these are modified. The L and P are not modified because they effectively come from the rotation and translation of the spatial part. And as we discussed that the spatial part of de Sitter is identical to the spatial part of flat space-time. So they are not affected by the Hubble constant or presence of a cosmological constant. However, the k epsilon, which is the mass multiple symmetry, they are indeed affected by the presence of a cosmological constant. Now let us take a different view at this problem. So we have arrived at the corresponding symmetry vector from one particular line of attack. Let us try to get the same from a different perspective as well. So for that, we can consider a linearized perturbation on the de Sitter background. So we have Einstein's equations and we perturb it about the de Sitter background. And we get the complicated looking wave equation, which is there on the screen. So the H tilde mu nu is effectively the trace reversed perturbation, which is often used in literature. And B mu is a short form for the covariant derivative of H tilde alpha mu in the de Sitter background. Now, of course, we need to impose certain gauge condition to make this equation simplify. And that gauge condition effectively corresponds to that the B mu should be related to -2 the Hubble constant times H tilde 0. So effectively, the identical gauge condition was also derived by the paper of Astekar et al. In 2015, when they were trying to compute the quadruple moment or quadruple formula for the gravitational wave emission in the context of asymptotically de Sitter spacetime. So, but that was done in conformal coordinates, while here we are following the standard cosmological coordinates in the context. Then it turns out, interestingly, that with this gauge condition, all of the perturbations decouple. The spatial part, the temporal spatial part all gets decoupled. The temporal spatial part or the both time part, that is not decoupled, but that can be decoupled by defining this new parameter H tilde. So the consequences of these equations would be important if one wants to generalize this approach to the case of Thorne, the way Thorne computed the multiple moments, and that is something we are currently pursuing of all. However, the multiple symmetry again emerges if we want to preserve the gauge condition. So we had a gauge condition that covariant derivative of H, the trace reversed perturbation, should be equal to -2 Hubble parameter times the H tilde 0. So that gauge condition we want to preserve. So that will of course change if I make a coordinate transformation, or in other words under diffeomorphism. So again, we want to preserve that gauge condition, which gives certain differential equations for this vector field xi. In addition, we know that the gravitational perturbations are also affected by the gauge choices. So if we want to eliminate the H tilde and H tilde 0i, so effectively we know that the degrees of freedom are often hidden in the spatial part of the perturbation. In that case, we obtain the two differential equations, which you can see on the screen, namely del 0 of xi 0 equal to 0, and another equation involving xi I and xi 0. It turns out that if you want to solve this differential equation in general, it leads to the exactly same vector field that we had derived from the harmonic gauge condition. So this provides a completely alternate derivation of the multiple symmetry vector. So that means that the multiple symmetry vector can either be derived from the harmonic gauge condition and the asymptotic fall-off condition, or from the perturbations, linearized perturbation in de Sitter as well. The connection between the two is not clear to us, that whether harmonic gauge plus asymptotic fall-off implies the gauge condition we are using for the linearized perturbation, but that is something we want to explore, and we are exploring currently. So having done all that, let us now get to the last part of the talk, that is, can we get the moments for the Kerr de Sitter spacetime? So I'll first talk about the spin multiple moments for Kerr de Sitter spacetime. So the vector field which generates the spin multiple moments, as I said before, is R cross gradient of the function epsilon. Now this epsilon can be expanded into spherical harmonics with YLM theta phi, and this is the vector LLM in that spherical decomposition. So it depends on a particular power of the R, and as well as it depends on BYLM theta phi. So this BYLM is effectively the magnetic part, so it stands for the R, the radial vector, cross grad of YLM. So YLM is a function of theta phi. It turns out that, unlike the case of Kerr, all even spin moments identically vanish, while all the odd spin moments are non-zero. And I have just quoted the first few spin moments for the case of Kerr de Sitter black hole. So as you can see that when H goes to 0, all of them reduces to their corresponding expression for the Kerr black hole, which is what we expect. Otherwise, this method would have failed. But now, in presence of a cosmological constant, there are non-trivial corrections of the order of the dimensionless parameter A times H. So, but since for the present day cosmological constant A times H is a small number, we do not expect to see any significant correction to the spin moments of Kerr de Sitter. However, if I go for the mass moments of the Kerr de Sitter black hole, we have done exactly the same thing. That is, we have spherically decomposed the parameter epsilon, and now the structure of the vector field is much more complicated, as it depends on both the electric part of YLM and the radial part of YLM. So electric part effectively says it is the gradient of Y, and the radial part means it's the radial vector with YLM theta. So this now have a radial component, theta component, phi component, and as well as a t component. Again, it turns out that if one computes the Noether charge for a Kerr de Sitter black hole, then all the even mass moments are non-zero, but all the odd mass moments identically vanishes. This is again up to our expectation because there is a symmetry of the Kerr de Sitter black hole about the equatorial plane. And I have again quoted the first few mass moments over here. And interestingly, they all reduce to the expression for the case of a Kerr black hole when the Hubble constant goes to 0. But in presence of a non-zero Hubble constant, there are corrections which now both involves AH, which is a dimensionless parameter, as well as H into T, which is another dimensionless parameter. It turns out that AH, as I said, is pretty small for the present day cosmological constant. But if you have a black hole which has lived long enough, then the time over here can be of the order of the Hubble time, inverse 1 over H, because age of the universe is like 1 over H. So T can be roughly some fraction of 1 over H. And as we see, that can lead to some significant deviation from that of the Kerr moments of the Kerr black hole, not for 0th order and 2nd order, but for higher order moments. So these moments are not currently directly observable using the gravitational wave observations, but hopefully in the future we'll have more direct observations which will be able to tell us the higher mass moments, and then probably we can talk about whether we are actually living in a de Sitter space-time and this correction whether they are making sense, and that will sort of tell us whether the formalism we have developed is correct or not. So I think I have finished. I will just end with my conclusion. So as I said, de Sitter space-time I have expressed in harmonic coordinates, and we did not find any literature on that. So I believe this is the first attempt to do that. Second, the residual gauge symmetry for de Sitter, that is, we should preserve the harmonic coordinates under coordinate transformation. That leads us to determine the multiple symmetry vector. Intriguingly, the same vector field appears if we consider linearized perturbations around de Sitter and even keep that gauge conditions to be preserved. Finally, the Noether charge associated with this multiple symmetry vector, we obtain the correct spin, and we do not know whether they're correct or not, but we obtain some mass and spin moments. They all reduce to the correct expression for Kerr black hole when H goes to 0, which gives us faith in them. And there are corrections to the Gerock-Hansen moments of the order of HT and of order HA, the only two dimensionless parameters which are available for the system. HA is supposed to be small, but HT need not be very small. Therefore, whether there can be some observable effects of this or not is something that we wish to explore in the future. So with this, I thank all of you for your kind attention, and any questions, please feel free to ask.
Okay, thank you very much. Thank you very much for excellent talk and perfect timing. We have still time for a few questions. Please ask if you have any. Sorry, but people are not so brave to ask question because it's very, very good. It's really very nice. I was enjoying to watch, to follow your talk. Thank you very much, Sumanta, again. Thank you. Bye.
Thank you.
Bye. And next speaker is Shailesh Kumar. Please stop, Sumanta, please stop sharing your screen. Okay, good.
So is the screen visible?
Yes, it's visible. It's fine.
Okay, okay. So shall I start now?
Yes, yes, now. Go ahead.
Yeah. Thank you. So I'm Shailesh Kumar. I'm a PhD student currently enrolled at IIIT Allahabad, India. And as a part of this parallel session, I would be presenting my recent works on displacement memory and BMS symmetries. So before starting, I would like to thank the organizing committee and the chairperson for giving me this wonderful chance to present my work at Marshall Grossman meeting. So the work based on basically on these references, these recent references. So let us start with the points. So gravitational memory effect, it is a well-known non-oscillatory part of the gravitational wave amplitude, which generates a permanent displacement for test particles or test detectors, which is being induced by gravitational waves. And it has not been detected yet experimentally. People are expecting to detect it in the coming decade using the advanced LIGO or laser detectors. It can trigger many intriguing and interesting finding of the black hole physics. So here, if you look at the picture, we have ring of test masses, and there could be two possible scenarios when the gravitational wave is not carrying memory and when the gravitational wave is carrying memory. So in the first case, when the gravitational wave is not carrying memory, we find that there is no relative change in the orientation of ring of test masses before and after the passage of the gravitational wave. Whereas in the second case, when the gravitational wave does carry memory, in that case, we find that there is a relative change. There is a permanent relative change in the orientation of ring of test masses before and after the passage of the gravitational wave. So the direct motivation for gravitational memory effect is coming from two perspectives. One is from the theoretical point of view, and another one is experimental point of view. So from theoretical perspective, memory effect is directly related to asymptotic symmetries of space-time, which were originally discovered by Vanderburg, Metzner, and Sachs, Bondi, Vanderburg, Metzner, and Sachs in the early 60s. And as a recent progress, Hawking, Perry, and Strominger conjectured that the BMS charges would help to retrieve the information in the information loss puzzle. So due to this, basically, recently, this recovering BMS symmetries near the horizon has become an active area of research. From experimental point of view, I mean, people are, as I mentioned, that the people are expecting to detect the memory part in the coming decade using the LIGO and LISA, which can find many intriguing properties of the near horizon structure of black hole. So all in all, I'm interested in finding the signatures of asymptotic symmetries on the test particles, which interact with the gravitational waves. So here, for this particular talk, I will be presenting a model scenario where gravitational wave carrying asymptotic symmetries will interact with test detectors and produce some permanent and persistent measurable effects. So here, these are the table of contents. I would be going through the horizon shell and BMS symmetries and how super translation and super rotation arise in the context of stitching of two black hole space times, and then memory effect for impulsive gravitational waves and for near horizon asymptotic space time. And then I will finally conclude my talk by providing the final remarks for the conclusion. And let us start with the horizon shell and BMS symmetries. So here, if we consider that we have two black hole space-times m plus and m minus with the respective coordinates defined as x plus beta and x minus beta, and we stitch them along a common null hypersurface sigma, and then common null hypersurface happens to be the horizon of the black hole. In that case, this analysis will basically generate a horizon shell, and we find that there's a singular term sitting in the Einstein tensor, which is proportional to this delta phi. And this will basically implicate that the null hypersurface will carry the impulsive gravitational wave and null matter. And these impulsive gravitational wave and null matter can separately be written as your impulsive gravitational wave degree of freedom gamma cap and null matter part gamma bar. And jointly, they can be written, of course, as a gamma AB. And later on, we will see that this will be containing your BMS parameters. And these physical scenarios, physical phenomena could be your violent astrophysical phenomena, nothing but supernova explosion or supermassive black hole mergers, which will basically produce your impulsive gravitational wave. So keeping in mind the consistency with the junction condition, we arrive at the surface, intrinsic properties of the singular null hypersurface, which is written in terms of your extrinsic curvature. So this is the intrinsic properties are nothing but surface energy density, surface current, and surface pressure. So now let us look at how this super translation arises in this context of stitching of two black hole space times. So this will basically motivate us to preserve the induced metric on the null hypersurface. And of course, the analysis should be consistent with the junction condition. So transformation, which will preserve the induced metric on the null hypersurface, will basically generate your super translation. So this would amount us to solve the Killing equation, which can be written in this form. And here, there could be two possible conditions when we, as a first condition, when we can consider that this spatial slice of the metric GAB. This is like two sphere metric, one can say. So here spatial slice of the metric does not depend on V coordinate. So in that case, this condition, if you demand that this condition, the del V GAB equal to 0, so we will be this ZV transformation, the transformation killing transformation along the V direction will be basically unconstrained, and we can have solution of this unconstrained parameter ZV of this sort, and further it can be written as V plus some function as your T in terms of your spatial coordinates. So this is what we call it as super translation. So this is what it is arising in the context of stitching of two space times. So further, if we try to recover the extended asymptotic symmetry, which is known as your super rotation symmetry, this can also be achieved in the context of black hole stitching of two black hole space times. So here we consider another condition when the induced metric on the null hypersurface to the codimension 1 of the null hypersurface metric. So this is special part of the metric that is will be basically depending upon your V coordinate, and this will this will basically will not allow us to write this particular will not allow us to have this particular freedom in the V direction, right? So what we do is that if we make the conformal transformation in the spatial slice of the metric, that is your Z and Z bar, and we write the killing equation, this one, in such a way, in a more compact form with the conformal factor omega in this form, then and we demand that this condition, this GAB induced metric, this is spatial slice of the metric basically does depend on V parameter. In that case, we can have one feasible solution of GAB, and this will give us a transformation of ZV, and which will compensate the transformation of conformal transformation we are making to the spatial part of the metric. So once we are making the conformal transformation to the spatial slice of the metric, as a compensating transformation we'll be having along the V direction, which will make sure that the metric remains preserved. So here the important point to note is that we should have our our parameter depending upon your V coordinate, because otherwise this will be 0 and there will not be any metric. The metric will no longer be preserved, right? So so this R parameter should depend on V coordinate. So this is how the super rotation appear in the context of stitching of two black hole space times. So let us look at the, so with this analysis, let us look at the intrinsic properties and super translation, super rotation. How does it appear for extreme and non-extreme black holes? So it has been already shown that the almost 70% of astrophysical and many supermassive black holes are near extremal. So more attention is required in order to explore their more properties. So the goal is to basically place the null shell unambiguously at the horizon. That will be our horizon shell, and we will try to find the BMS intrinsic properties of the horizon shell. So here for extreme RN case, we find that the spatial slice of the metric will be nothing but our theta and phi coordinate, two sphere metric, and this will give us super translation. But as an important point I mentioned earlier, that this R parameter, we can see that it does not depend on V coordinate, right? So this will basically tell us that the super rotation cannot be recovered. And of course, we can achieve the intrinsic properties of the horizon shell, which will be written in terms of your super translation parameter. And here I'm mentioning the surface energy density. There will be surface current and surface pressure in terms of super translation parameter. And for in contrast to this extreme ion case, in the square shell case, we have zero surface current and surface pressure, but surface energy density can be restored in terms of BMS parameters. And there in the critical coordinate of your square shell black hole, we have R parameter in terms of U and V. So V parameter is there in the R coordinate. So that is why we can recover the super rotation in that case, but not at the horizon, just a little away from the horizon. So let us look at the memory effect for the interaction of impulsive gravitational wave and time-lag geodesics. So here we consider that when the two nearby time-lag geodesics are crossing the null hypersurface or the horizon shell, they will interact with the impulsive gravitational wave, and there will be a permanent relative change in the displacement vector. So this is what this will be captured by the your deviation, geodesic deviation equation, and the jump will be the memory part will be captured in the Riemann tensor part. So, and we compute the deviation vector to the linear order of u. So this will be a local effect. So here, as a result, we find that find the spatial deviation vectors xa. So for spherical coordinates, it is nothing but x theta and x phi, and there will be another component xv of the deviation vector, and these gammas will basically contain your BMS parameters, which are nothing but your sum of your impulsive gravitational wave and null matter part. So we have provided our result for squash and extreme RN case. So as a result, what we find that the before passes of the impulsive gravitational wave, there will be a initial separation between the two nearby time lag geodesics. And when it interacts with the impulsive gravitational wave, there will be a change in the relative change in the displacement vector or deviation vector. And in the squash case, we find that the surface current, since the surface current is zero, so displacement will be having within the surface. Whereas in the extreme iron case, we find that the displacement will get displaced off from the initial 2D surface just because the surface current is non-zero. And here I have written one component, and other related results can be seen in these two references. And here gamma will be capturing your BMS parameters T. And this is what like telling us the memory effect in the context of stitching of two black hole spacetimes when the impulsive gravitational wave interact with your time lag geodesics. So now further, let us look at the memory effect for near horizon asymptotic spacetimes. So here, as we already know, for the conventional memory effect, which arises due to the interaction between gravitational waves and test detectors near the fusional infinity, and the obtained shift between detectors can be reproduced by a super transition. So that is what happens with the near null infinity case. So we had two detectors and they will interact with the gravitational wave, and there will be a change in the separation of this displacement vector, and that is what being captured in the geodesic deviation equation. So here I have mentioned. And this study, I mean, it is well known and has been extensively studied by Strominger and Zibotov from theoretical point of view, of course. And what our goal is to provide a similar study of memory effect near the horizon of black hole. So here we have placed two test detectors near the horizon of black hole, and they will be interacting with the gravitational waves near the horizon of the black hole. And as a result, we are aiming to find the change in the displacement vector of the test detectors before and after the pass of the gravitational wave, and that will carry basically that will also carry your BMS parameter in the shift associated with the change in the displacement vector. So all in all, the important point is to look at the geodesic deviation equation. So let us look at this near horizon asymptotic form of the 4D metric. So this is details of this metric and the conserved charges and all transformation of the metric parameters can be seen in the Donny et al. Papers. So here we have this near horizon asymptotic form of the 4D metric, and these are the following fall-off conditions, and this asymptotic structure of this metric will be preserved by asymptotic killing vectors, and the metric parameters along the killing direction will be having this sort of transformations. So here the other metric parameters, of course, this theta a and omega can also be also have transformation along the killing direction chi. But here we are mentioning the relevant transformations for our purpose in this talk. So here there are two possible scenarios when we can consider this kappa to be constant, finite constant, and when the kappa is tending to 0. So there, and we can of course get the solution for f. So there are two possibilities. Let us look at that. So here for constant kappa, we get solution of this function f written in this form, and this kappa tending to 0 case can be written in this form. So here in contrast to the far region case, what we find is that we can recover two super translations t and x together with one super rotation y, which I had mentioned here. So here these transformations basically ensure that the metric will remain preserved. So that is main distinguishing feature from the far region memory effect, or you can say far region BMS analysis. And for these two separate cases, we have provided our displacement memory and its connection with asymptotic symmetries. So as a result, for this metric, we have this geodesic deviation equation, and the solution of the geodesic deviation equation can be written in this form. And this we need to write only the Riemann tensor here. So we have mentioned only one component of the Riemann tensor, and similarly, one can write, of course, the another component of the Riemann tensor. And these steps, these computations also ensure that the GVA component of Einstein field equation will basically tell us that this theta A component of the metric parameter. So this will basically will be function of only your spatial coordinates, that is your zeta and zeta bar. So now further, if we put our other component of the Riemann tensor, we will finally get the compact form of the geodesic deviation equation solution, which we can be written in this form. And this is our basically the displacement memory. And here to compute this, just further to look at one more property, that this delta lambda zeta zeta bar, delta lambda zeta zeta, can be computed using the Shockwave profile of stress energy tensor of this form. And we will get the delta lambda expression from this Einstein field equation containing your G tilde, and G tilde can be written in this form H, and we have seen that here this H is nothing but written in terms of theta zeta. So here the important point is that this memory, this displacement S zeta bar is basically related to your metric parameters, because this lambda and theta are also interrelated with each other, right? So here I've written only one component of the geodesic deviation equation. There is another possible component of the geodesic deviation equation solution, that is your delta S zeta. So this is this completes our displacement memory basically. So in order to relate it with the BMS symmetry, so what we do is that we here see that this delta lambda is basically independent of V coordinate, right? So here this is changed delta V, it is a constant, it does not depend on your V coordinate, right? So so since we have looked at the transformation of the metric parameters, so once we have this delta lambda, so we will also try to see that the transformation of these your metric parameters, your delta chi lambda we have seen in our earlier slides. So those transformations along the killing direction should also be independent of V coordinate, right? So so here, as we have seen that this, there will be change in the delta lambda AB components, all possible components. So we can, once we have this delta lambda AB, we can write the general solution of lambda AB. And once we have the solution of lambda AB, we can write the variation of lambda AB along the killing direction. So here I'm mentioning only one component. There will be two other more possible components, and we can try to find the super rotation YC, that is the word Y zeta and Y zeta bar and X. So in principle, three equations are there and three unknowns are there. We can, in principle, we can determine the relation between super rotation and super translation, which will account for the same shift in the delta lambda. So, but it is quite difficult to obtain the solution of this equation, these equations. So here what we do is that if we freeze the super translation parameter X, we obtain a super rotation solution Y zeta of this form, which will basically tell us that the super rotation will basically restore the displacement memory in terms of your BMS, extended BMS symmetry, right? So this will compensating your delta lambda shift basically. So here we have also provide our study for a kappa tending to 0 case. This can be seen in our result, this one paper, this one. And further, just last as a last result for this, we are just trying to take here the reduced form of the metric, where the metric, where the asymptotic form of a near horizon metric of a spherically symmetric black hole can be understood. That the spatial slice of the metric has been deformed, and with the GVA metric component to be 0, and the reduced form of the metric will be of this form. And we are just analyzing here this kappa tending to 0 case, and we have the solution for deviation vector. And this delta lambda again AB components can be found using the Shockwave profile of the stress energy tensor using the Einstein field equation. and the solution can be written in this
Excuse me,
form.
Shailesh,
Yes,
you
yes,
spoke
yes, yes.
20 minutes.
Oh,
How
just
many
1 minute.
minutes do you need more?
Yeah, just 1 minute. After this, just
Okay,
conclusions.
good. Thank you.
Yes, yeah, thank you. So here we have a similar form of the equation as it is proportional to rho, and whereas in the far region case we find 1 proportional to 1 by r. So it is a similarity with the far region. And to relate it with the BMS symmetry, we have, once we have the delta lambda solution, we can write the lambda solution, and the variation of lambda AB can be written in this form. Again, the solution is very difficult to obtain to compensate this delta lambda shift in the geodesic deviation solution. So what we do is that we freeze the super rotation and find the super translation solution, which will basically induce the same shift in the displacement memory. So this is the analysis for a reduced form of the metric. So finally, as a conclusion, we have seen the horizon shell and the super translation and super rotation, how it arises in the context of its stitching of two black hole space times. And we recover 2 super translation and one super rotation in contrast to the far region case. And we have provided our analysis for general asymptotic near horizon asymptotic form of the metric, and which mimics basically for particular case when kappa tending to 0 to the memory effect which is proportional to 1 by r in the far region case. So for future prospects, we are looking at the problem for more observational perspective using from PN theory and lensing effect for detecting this BMS memory. So this basically provides us a rich structure of near horizon, could be useful as a model scenario, not only for theoretical, but also from experimental point of view. Thank you. I would be happy to take the questions, and sorry for exceeding the time.
No, it's okay. It's we have. Thank you very much for a very nice talk, but we have still time for 1-2 short questions and short answers.
I see.
If there are any questions.
Yes.
So, at the moment, I do not see questions.
I see.
In this case, let us thank speaker again. Thank you very much.
Thank you. Thank you.
Next speaker is Shilpa Sarkar.
Yeah.
Please share your screen. Okay, good. Full screen, please. Okay, good.
Shall I start? Shall I start now? Hello?
Full screen, please, because it's you. Now you are not in full screen mode. Okay, good.
Yeah, you can hear me, right?
Yes, we are hearing you. It's fine. Okay. Everything fine. Please go ahead.
Okay, thank you.
Thank you.
Yeah, I'm Shilpa and I'm from Aries, Nainital, India. And the topic I'm going to cover and talk about today is about the accretion flows around compact objects, especially the 2-temperature accretion flows. So compact objects like black holes, neutron stars, and white dwarfs, features is their extreme small size. So this is quantified using a ratio called the compactness ratio, which is the mass of the star to the radius of the star. And because of this extreme compactness ratio, they exhibit a phenomena called accretion, which is the accumulation of matter from the surrounding medium due to the strong gravitational potential energy. So this accretion mechanism is the best known mechanism till now to explain the high luminosities and energies of X-ray binaries and AGNs. So there is a need to model these accretion flows in order to understand the underlying physics present in these systems. So these models have been improvised from time to time, mainly to match with the latest observations. Thus, we keep few basic elements in mind while modeling accretion flows. First of all, these flows are transonic in nature. That is, they have to pass through at least one sonic point. And if we are working on black holes, then we should consider the general relativistic regime. And since we are dealing with the flows which are transrelativistic in nature, we need to consider a relativistic equation of state, and fixed adiabatic indices is untenable. And there should be advection inside the system because it induces stability, and all this has to be solved self-consistently using the equations of motion. Now comes the question about the types of species that are present in the flow, because it will determine the thermodynamics of the system. So hydrogen being the most abundant element in the universe, and ionized plasma consists of protons and electrons. And there could be many conditions which will determine the temperature of these species. So first of all is the difference in the masses. So mass of the proton, as we know, is 1,000 times larger than the mass of the electron. So it is obvious that their temperature could be different. The second point is that the unfold timescales are generally shorter than the Coulomb coupling timescale. So this condition has been found to be true in most of the astrophysical cases. So this condition means, or the Coulomb coupling timescale means, the timescale in which the electrons and protons, they interact and settle down into a single temperature distribution. So before that, the electrons and protons, they get attracted towards the central object. Or in other words, this means that the electrons and protons are thermally decoupled, or the proton and electron temperature are not same. And third point is that electrons are the main radiators. So all the emission mechanisms, they generally act on electrons more. So their temperature is bound to be different from the protons. So in general, astrophysical cases, a flow is necessarily of two different temperatures, one temperature defining protons and one temperature defining electrons. So these types of flows, which is two temperature flows, are more realistic in nature as well as generic in nature. And since we have information about the electron temperature, it helps in computing the spectrum. So we did the spectral analysis around compact objects using these two temperature flows. Now there could be one temperature flows as well, because a lot of work has been done in one temperature flows, where people have considered that the Coulomb interaction between the protons and electrons is very strong, allowing them to settle down into a single temperature. That is, the proton and electron, they share a single temperature. So this regime helps in simplifying the equations, as well as they do not allow us to get involved in the more complexities of the situation of the system, and we can extract all the essential qualitative features. So many people have worked into one temperature regime. So in this one temperature regime, defined by a temperature which is theta, we get a unique sonic point and hence a unique transonic solution. But working in two temperature regime, we now have two different temperatures, one temperature defining protons and the other electrons. But there is no known principle which is dictated by plasma physics which may constrain the relation between these two temperatures, or the number of equations is conserved, but we have an extra temperature, but no extra equation which can couple these two temperatures. Hence, these equations are not complete and the system is degenerate, which means that for the same sets of constants of motion, we get infinite solutions. And this is what nature should not prefer, because a space of constant motion should have a unique solution. So this degeneracy has been given from time to the previous works. So they dealt away with this degeneracy by parameterizing the proton and electron temperature, or a few works also assumed either proton temperature or electron temperature at any point of the flow, and even specific relations were introduced so that an extra equation helps to deal away with the extra variable. But all these choices were arbitrary, and solutions obtained can give us a wrong information of the system. So we attended and solved this problem of degeneracy and proposed a novel methodology to remove or constrain this degeneracy. So we attended solved the problem of degeneracy first in the case of black holes. So here you could see a Mach number plot where the solid line is the global accretion solution, and in the right hand side we have the spectrum, and all these solutions are for the same sets of constants of motion. So we can see that few solutions pass through outer sonic point, few have shocks, few pass through inner sonic point, and correspondingly the spectrum also changes. So it is important and necessary to constrain this degeneracy, otherwise we could end up with the wrong information of the system. So what we did is that from the first principles we obtained an entropy form. So this is the entropy measure form which we derived from the first principles, and using this entropy on all the degenerate solutions means we measure the entropy of all the degenerate solutions. And from the second law of thermodynamics, as we know that nature prefers a solution with maximum entropy, we constrain that degeneracy. So in the previous animation which I showed, we measured the entropy of all the solutions and saw that the maximum entropy solution was this one, where the global solution passes through an outer sonic point and then harbors a shock and then passes through the inner sonic point. So the sonic point is around, means Mach number 1, where the velocity is equal to the sound speed. And this and the right hand side, we can see this is the corresponding spectrum. So for these constants of motion, this is the correct solution. So not only black holes, but neutron stars in two temperature regime again poses this degeneracy problem. And these are the constants of motion, and we have a different Mach solutions represented by Mach number plot, and in the right hand side we have the spectrum. So the black dots and triangles are the sonic points. So again we constrain the degeneracy by applying the entropy measure form we proposed, and this is a maximum entropy solution. So the difference between black holes and neutron stars is the inner boundary condition, because black holes insist that matter should cross the event horizon at the speed of light, while for neutron star, because of the hard surface, matter has to come to a stop. So there is a strong shock jump just near the neutron star surface, unlike in case of black holes, which we saw achieve the speed of light near the horizon. So since this session is about the black holes, so I will discuss the few important results which I got for accretion flows around black holes. So these are the typical two temperature solutions around black holes and the flow variables and the spectrum. So this solution is for these constants of motion, and it has been obtained from after maximizing the entropy. So in this plot, the green solid line is a Mach number plot. Here we can see this is the radial velocity, where we can see that near the horizon, the matter velocity achieves the speed of light. This is the number density. This is the energy. This energy is the generalized Bernoulli constant, which is actually a constant of motion even in the presence of dissipation. And this is the temperature, where the dotted line is for the proton temperature and the solid line is the electron temperature. We can see that very far away the proton and electron temperature are almost the same, but as matter gets accreted towards the black hole, the radiation processes, they mainly act on the electrons, and the electron temperature, they deviate much from the protons and are have lesser values than the protons. This is the adiabatic index. So we have used a relativistic equation of state with variable adiabatic index. So it smoothly varies with the radius. So very far away, protons and electrons both are almost non-relativistic. That is, gamma is around 5/3. But as matter is accreted, the protons, they become sub-relativistic, but the electrons, they become relativistic because of their less mass. So relativistic means that the gamma index has approached 4/3 value. And this is the corresponding spectrum. So this power law part is mainly because of the inverse comptonization of the soft photons present in the system. And the higher frequency part is contributed mainly by Bremsstrahlung, and this hump is mainly because of the synchrotron emission. So when we investigated the contribution of different regions of the black hole accretion disk to the total spectrum, so we divided few regions and plotted the corresponding spectrum. So the regions are marked here. So as we know that as we move far away from the central object, the temperature decreases. Here we can see the same thing, that the temperature decreases as we move far away. So the luminosity also decreases. We can see that the luminosity from 3 to 5 is more than 5 to 8 and so on. But very near the black hole, from 2 to 3, the luminosity is also decreasing, although the temperature is higher. So this is mainly because of the photon trapping effects working very near the black hole event horizon, such that the photons are unable to escape and capture. So when we tabulated all the contributions from different regions, we see that 90% of the total luminosity actually comes from a region less than 10 special radius. So we also investigated the change in spectrum with black hole mass and accretion rate. So here in the y-axis we can see the luminosity, and in the x-axis it is the accretion rate, and different circles represent the different masses of black holes. So small is 10 solar mass, then 10 to the 3, and then 10 to the 6. And this color bar is the spectral index, that is the power law of the inverse quantumized photons. So for a given accretion rate, when we change the mass of the black hole, we see these are the corresponding spectrum. So we see that the spectral index of all these solutions does not change much, and the overall spectral shape is same, but the bandwidth increases. So there is a large amount of flux for a higher mass black hole in the radio regimes, which actually allows us to probe black holes like M87, which has a higher mass in the radio regimes. And keeping the black hole mass same and increasing the accretion rate, we can see that the bandwidth doesn't increase much, but the spectral index increases. This is mainly because of the increased amount of inverse quantization, which makes the spectrum harder. And when we computed the efficiency of all these solutions, we see that with increase in accretion rate, the efficiency increases, tapering off at 10%. But with black hole mass, it doesn't change much. And the spectral index, as we have seen, that with increase in black hole mass or with increase in accretion rate of the system, the spectral index becomes harder. So here we have a darker red color. So here I finish my talk with the conclusions, that is, degeneracy is a generic problem. It doesn't depend whether the compact object is a black hole or a neutron star or a white dwarf. And the proposed methodology to remove degeneracy doesn't apply only to these two compact objects, but it applies to all other objects in the two temperature regime. And the rest of the conclusions I have discussed before, that most of the emission comes from a region very close to the black hole. And with the increase in accretion rate or black hole mass, the system becomes more luminous. So thank you.
Thank you very much for very interesting talk. Thank you very much. We have time for questions. If there are no other questions, I would like to ask you a question. You presented very nice theoretical studies, but could you list some, let us say, observational facility which could, let us say, confirm your theoretical study, to confirm some theoretical prediction of
I have
some theoretical prediction? Thank you.
Not matched my these spectrums with the observations, but I will do it now because of the because I have collaborated with few people to match with the these spectrums. But for the time being, I haven't done much because we were more concerned with removing the degeneracy inside this solution, and which was actually a long outstanding problem in this field. So I haven't done any observational work till now.
But by the way, it's as I understood your answer, so at the moment you are not ready to compare your theoretical, let us say, calculations with observational studies. But by the way, probably you have some, let us say, you have some observations and forthcoming observations where your theoretical studies may be relevant for them. So
okay, so mainly I match the observations in the sense that I match these luminosities for these black hole masses and the efficiencies. So overall the orders are same. Apart from that, since I have the spectrum, I can match it with the observation, but I haven't matched. So the luminosities and the efficiencies, they generally come around like 10%, or luminous means a higher black hole mass has a higher luminosity. So that is consistent with observations, but the exact matching I haven't done.
okay, thank you very much. If there are no other questions, let us thank speaker again. Thank you. Thank you very much.
Thank you.
And the next speaker is Dr. Stanislav Komarov. Please share your screen.
Good morning.
Good morning.
Now I will be ready.
It's not full screen mode, or it's full screen in your presentation?
Full screen I have, but I think I can share my image.
It's only first page.
Yes, it's okay.
But, could you change slides in your presentation?
Yes, and can you see my presentation?
Yes, but please full screen mode. Yes, that is better.
Good morning for the second time.
Okay, good morning.
And my work, reconstruction of a star motion in the vicinity of black hole from the redshift of electromagnetic spectrum. My name is Komarov Stanislav, and work was performed with Professor Alexander Konstantinovich Grubatsevich. We are from the Belarusian State University. And let us start with introduction. It is well known from observational data that in the center of our galaxy exists supermassive black hole with mass about 4 million solar masses. And apart from this, there are large star cluster near the supermassive black hole. This star cluster is called as cluster. And there are stars in this cluster that moves on very small orbits around a supermassive black hole. For example, such star as S62 has pericenter distance is about 600 masses in geometrical units of supermassive black hole. And due to this, it is possible to investigate motion of the stars and to test theories of gravity when we observe certain electromagnetic characteristic of radiation that come from these stars. From the observational point of view, it is more simple and more convenient to use redshift as such characteristic, because of redshift can be measured with very high accuracy. And apart from the stars of S cluster, there is a large population of pulsars, X-ray pulsars near the galactic center. This image from nature, this non-thermal sources of radiation that is presented is as blue circles. They correspond to radiation of accreting neutron stars. Most of these can be seen as pulsars. And also we know that pulsars are very stable sources of pulsed electromagnetic emission, and due to this it is possible also to obtain very useful data from measuring such pulses of electromagnetic radiation. And it will be seen in the presentation that such characteristic as redshift and time of pulses of pulsar can be described in one mathematical shape. Because of these characteristics are connected very simple between each other. And our main theoretical model that we plan to apply to the investigation of motion of the stars is the following. We consider, for the first time, we consider non-rotating Schwarzschild black hole and consider one point source that moves around the black hole. This source can emit electromagnetic radiation that propagate also through external gravitational field of this Schwarzschild black hole. Observer detect this radiation and he measure redshift of electromagnetic radiation. And firstly, we must solve the direct problem, is the obtaining of redshift function from known motion of the source star. And secondly, we solve inverse problem, obtaining parameters of motion of the source star from the known redshift data. For this purpose, we use well-known analytical solutions in Schwarzschild geometry. Firstly, this solution for time-like geodesic that represent motion of the source star. From this solution, we can express radial coordinates, for example, as function of azimuthal angle on the orbit phi, and truth parameters of motion of the source star. This is pericenter distance p1 and apocenter distance p2. Alternatively, this function can be expressed through energy, mechanical energy of the point source, and angular momentum L. And also we use well-known solution for isotropic geodesic in Schwarzschild space-time. This solution consists of parameters of motion angle theta and depend on parameter of motion P or D. D is the impact parameter of the ray, and it is known that this impact parameter is not a function of parameters of motion of the star. It's not explicit function parameters of motion of the star, but in order to obtain this impact parameter, it is necessary to solve boundary value problem. This boundary value problem, our isotropic geodesic must intersect both. This must intersect time-like geodesic of the source and time-like geodesic of the observer. In other words, this is a solution for geodesic equation, is isotropic solution that must intersect these 2 points. And this boundary value problem reduced to non-linear usual equation, and due to this, we cannot express impact parameter D as explicit function of parameters of motion. We only can use it as implicit function of parameters of motion of the star. The following formulas represent redshift as function of velocity of the source and velocity of the observer, and wave vector in the point of the source and wave vector in the point of observer. Velocity of the source star is expressed through parameters of motion of this star, but wave vector is depend on these parameters only as implicit function, as I mentioned already. And the following string is the equation that expressed times of arrival for pulses of pulsar. And from this formula, it is clearly seen that this function is very simple, depend on redshift of time, but also one more parameter that we do not know. We have this is pulsar period is the reference frame of the pulsar. But from this, we will solve our problem only for one function for z. And setting the generalization of the method can give us possibility to solve the analogous problem also for times of pulses of pulsar. Firstly, we consider analytical expressions for the wave vector of the source of the electromagnetic radiation that propagate from the source to observer. And also we must write down a formula that connect of time of observation and proper time of the source star. This can be calculated through integral, and by using this formula, it is possible through observational data to obtain graphic of redshift as function of proper time. Not only as function of time of observer, but also as function of proper time of the source time. This is example of the solution of direct problem. Redshift as function of time of observation. The parameters of motion of the source star presented here. Recenter, apocenter distance, and inclination of the orbit. For the solution of inverse problem, in literature, there are following approaches. For example, it is using of ordinary statistical mathematical methods that are use chi-square function. It can depend not only redshift, but also, for example, from observational position of the stars. This formula is from the following article. But in most cases, only redshift is used due to observational position of the stars is measured with much less accuracy, but redshift can be measured with high accuracy. We know that redshift function is not explicit function of parameters of motion, and due to this, we propose another approach for the solution of inverse problem. For this purpose, we use not only redshift function, but also its derivative relative to time of observation. For this purpose, it is necessary to consider congruence of isotropic geodesics that follow to observer. And in order to consider such congruence, it is useful to use Newman-Penrose formalism to introduce Newman-Penrose tetrad. This is standard formulas we have for this. This is formula for redshift. And it is possible to calculate derivative of redshift relative to time. We obtain such expression. And it is seen from this formula that expression is dependent on two optical scalars, rho and sigma. They have physical meaning. The following: sigma is the influence of gravity on the shape of the image that is formed by congruence of the tropic geodesics, and rho is the influence of external gravitational field on the magnification of image. And it is known from numerical calculations that sigma is much more less than rho, and due to this we can neglect by this parameter. And physically this means that we neglect neglect to influence of external gravitational field on the shape of the image. Solution of the obtained system of equations we can obtain if we derive impact parameter from the formula for redshift and the formula for its derivative. And simply we write equality between obtained expressions. We now obtain the following equation. That functions that only parameters of motion, radial coordinates, and angle on the isotropic geodesic. And after certain manipulations, we can derive the following formulas. The first formula we also can use for applying standard less square method, less squares method for the solution of inverse problem. And another expressions we can use also to obtain starting value for the inverse squares method. In papers that were presented here, there are no approaches in order to obtain starting value for the solution of such problem, but using these equations, because of they do not depend on impact parameter d, they can be applied to obtain two equations with 5 unknown variables. These unknown variables, this is energy, momentum, inclination angle, initial angle on the orbit of the source, and also initial time of pericenter passage of the star. After this, we can write down such surfaces. No, this is not surfaces in 5-dimensional space, but they are they are only shares of the surfaces in two dimensional space, pericenter and apocenter distance. And through these surfaces, we can find point of intersection of the surfaces that correspond to exact solution for parameters of motion of the star. And applying this method, we can obtain the following results. The first column in this table is the exact solution that is we use in our theoretical model. The latest column is the exact values I'm sorry. The last column is the exact model that we have in our theoretical model. The first column is the solution that is we obtain from the graphics that are presented in the previous slide. And the second column is the reconstructed value of the parameters of motion that are obtained after application of standard least squares method. And it is seen that we obtain quite good accuracy for the solution of the problem. And thank you for your attention.
Thank you very much for your talk and excellent timing. If there are any questions, I invite people in the audience to ask questions. If there are no other questions, I would like to ask you a question. First, about some remark. You quoted Zhang et al. Paper when they considered Kerr metric to analyze trajectory of bright stars near the galactic center. But you have to keep in mind that if there is only black hole, rotating black hole, that is excellent approximation. But of course, you have some extended mass distribution in stellar cluster and plus probably dark matter distribution, because astroparticle physicists are saying that there is a dark matter distribution also in addition to stellar cluster. But for sure, there is a stellar cluster. It means there is a black hole, rotating black hole, plus stellar cluster. In this case, it's not Kerr metric, of course. There are some deviation. But question is how strong are these deviation? And also I have a question. You considered gravitational redshift, but both gravity collaboration and Keck found some, let us say, relativistic gravitational redshift 3 years ago near pericenter passage of S2 star. Could you apply your technology to calculate gravitational redshift near pericenter passage of S2 star? That is question.
Yes, thank you for your remark. And that is related to the question. Certainly, yes, we plan in future to apply our technology to analyzing of motion of a star. For example, the question is a star has quite a large distance from the supermassive black hole, and due to this, maybe general relativistic effects can be not seen such clearly, but we know that with time many new stars is observed. For example, S62 star that was considered on the first slide. This star has a smaller distance to supermassive black hole, is about 10 times, if I remember. But certainly S2 star else is interesting object for applying of our technology. We plan this. Yes.
Okay, thank you very much. Other questions? I do not see other questions. People do not raise their hands. In this case, let us thank speaker again. Thank you very much.
Thank you.
Thank you. And last speaker of this morning session will be Julian Westerbeck. Please stop sharing your screen. Stanislav, please stop sharing.
Yes.
We are still seeing your screen.
I also only see the screen.
No, it's we are still. You have to stop your to share your screen. Okay, I did it. Okay, Julian, please share your screen.
Yes. Can you see a green building?
Yes, it's fine.
Thanks.
Go ahead.
Okay, then. Hello also from me, and good morning from where I am. And first of all, let me thank you for the opportunity to present here this work on the observation of a multi-mode quasi-normal spectrum from a perturbed Kerr black hole, from a perturbed black hole so far. This is a work with a number of collaborators from a number of different institutions, and what we report here is the first observation of multiple angular modes from the ring-down spectrum of a black hole. And we find strong evidence for the presence of at least two such modes in the ring-down signal. You can find the current version of this work on arXiv. And let us first maybe quickly review the form of the ring-down signal. On the left, you can see a popular representation of the full gravitational wave signal of two merging black holes that starts with the in-spiral phase, then continues to the merger phase, and finally the ring-down phase, where the perturbed black hole settles down to its final Kerr state. And on the right, you see that waveform with the in-spiral and merger part grayed out, and only the ring down part remaining that we're interested in. And the ring down consists of quasi-normal modes, a superposition of these modes that are damped sinusoids. And you can see a formula describing these below that plot. And each individual damped sinusoid is determined by 4 parameters. And those are the frequency f and damping time tau, which are determined by the mass and spin of the black hole, and also its amplitude and initial phase, which are determined by the initial perturbation. And this spectrum is decomposed in spheroidal harmonics and is thus enumerated by indices L and M, which are the usual angular dependency, and an additional index N, the overtone number for sinusoids that share the same angular mode, but there's a number of different quasi-normal modes for each angular mode. And you can also see in that formula the factor from the spheroidal harmonics affecting the relative amplitudes of the modes that you can observe depending on the orientation of the black hole with respect to the line of sight to the observer of the signal. So the idea of black hole spectroscopy, as it's called, is to measure such individual quasi-normal modes from the ring-down spectrum and determine the parameters. And reminding of the no-hair theorem, we know that a Kerr black hole, that is an astrophysical, thus negligibly charged black hole, is entirely characterized by its mass and angular momentum. And this prediction is testable by observing at least 2 different modes of the quasi-normal mode spectrum, and then comparing the consistency of the parameters. That is, you can measure for one mode the frequency and damping time, calculate the corresponding mass and spin, do the same for a second mode, and then check the consistency between these mass and spin estimates, or do one more transformation from mass and spin back to frequency and damping time and compare these between 2 modes. The excitation of higher than the fundamental, that is the 2-2 mode, however, is generally small and depends on the initial perturbation and in particular on the mass ratio of the binary black hole. And predictions based on theoretical population models on the left and the observed population as seen by LIGO so far on the right were made, and we're trying to find out how many events per year of collected data could be expected to be usable for such a test. So where you could measure sufficiently well at least two of these modes. And on the left, you can see the lower curves correspond to the events where such tests would be possible. And advanced LIGO is the third point from the left, where you can see that with detectors of the state that they are close to now, you would expect to be able to do this only once in tens of years of data. And on the right, our results are suggesting similar rates. So to do this on a reasonable time scale, these analyses suggest that you would need more sensitive detectors, at least of the Voyager, that is the final plausible upgrade of the current detectors, or third generation detectors. Yes, to do this test on a reasonable time scale. However, then came GW 190521, which is the most massive binary black hole merger detected by LIGO so far. And importantly, the mass range for this was not included in the population model predictions that we just saw. And the LIGO detectors have a sensitivity that is depending on the frequency. And for this event, due to its high mass, the signal lies in a frequency band such that the ring down actually contains a large amount of the total signal to noise ratio. Whereas for the events with lighter black holes, usually the inspiral merger parts contain the larger amount of the signal to noise ratio. So to see what we can find out about the quasinormal modes of this event, what we do is first we have to remove the inspiral and merger part of the signal that you can see on the left. We see that there's the data stream and the times before the merger are being removed with only the ring down signal remaining. And on this remaining data, then we perform three different analyses. The first is what we call an agnostic analysis, where we just assume that a signal is present containing two independent arbitrary damped sinusoids. There's no particular relation between the parameters of the two. And if we find some candidate with this, then we can do a second analysis where we indeed do assume the correlation between the parameters of the individual modes. And we can use this to quantify the probability of modes of the curring down being present there. And finally, if this works, then we can impose the same relation again. However, we can add a deviation that is allowed for and test whether the deviations from the predicted parameters are supported by the data. So for the first analysis, that is the agnostic one, we have these two arbitrary damped sinusoids, and we divide the data up. So we divide the parameter space up into two frequency ranges. We do this because otherwise the two damped sinusoids in the model waveform would switch their mapping between the data features that they find and the particular part of the model waveform. So there would be a degeneracy that we remove in this way. And if we do this, we find that in a frequency range that is called A here, we find a damped sinusoid that is very well measured with very well constrained parameters. somewhere close to 62 Hertz and also with a well-measured damping time. And in frequency range B, which is much broader, we also see a clear damped sinusoid mode that is visible there. It is broader in parameter space because it is a quieter part of the signal, so it is not as well constrained, but there's clearly something there that matches the damped sinusoid template. And now we can use the Kerr prediction if we assume that what we see in range A is the fundamental mode, the 220 mode. Then we can have a prediction of the expected parameters for other modes in the spectrum. And if we do that, we see that indeed this mode in the second frequency range matches very well with the expectation for the 3-3 mode when we assume that the dominant mode is the 2-2. And indeed, that also matches our expectation of the 3-3 mode being the second loudest mode in this case. So now we want to quantify the probability of this signal being the Kerr ring down. And for that, we impose the relation between the parameters as expected from general relativity. And to quantify the preference for different models, we use the Bayes factor, which simply is the ratio of evidences for one model versus the other model, which is to be compared against. And then we can select the preferred model through this. And on the left, you can see a table suggesting the interpretation of values of this Bayes factor, saying that in a range of 10 to 100, this should be considered strong evidence for one model versus the other. The Bayes model we compare against is a model assuming the presence of only one mode, the fundamental one. And on the right, you can see the Bayes factors for different models compared to this single mode model, where we have different combinations of modes in the model that we compare with the fundamental only. And as there is some uncertainty in the exact merger time of the event, we perform this analysis at different times after this merger time. And you can see that for the dark blue, the 2-2 and 3-3 mode model, there's a number of times where we find this strong evidence, and there's a peak at a Bayes factor of around 40 in favor of these two modes versus only the fundamental mode, and the other models there generally find smaller support. So this is a nice result, and what we can do with this now is, well, first, of course, we can just show the recovered waveform and see that it indeed matches the data on the left. But one thing we can do with this result that we have found the mode now is we can get an independent measurement of the final mass and spin of the black hole, independent from the in-spiral merger and ring down waveform, that is, based solely on the post-merger signal. And on the right, you can see that where the final mass and the final spin of the black hole are shown, and they are centered around 330 solar masses and a dimensionless spin of around 0.87. And of course, the values for the 2-2 and the 2-2 and 3-3 mode models agree very well there. So this is an independent measurement of the final mass and spin. And another such independent measurement that you can do is on the mass ratio of the components in the binary black hole. And you can do this by using the amplitude ratio of the individual modes. On the left, you can see a fit to numerical relativity simulations, which gives a prediction of the amplitude ratio between the two modes. for different mass ratios, in this case for quasi-circular and aligned spin binary. And on the right, you see the measurement of the amplitude ratio. So the ratio between the 3-3 and the 2-2 fundamental mode amplitude that we found from our analysis. And on the lower right panel, this is converted via these numerical relativity fits to the corresponding mass ratio. And you can see that it peaks around a value of 0.4, so indeed unequal masses. And also shown are previous results using the full in-spiral merger and ring down templates for the signal. And you can see that there indeed is some tension between these, as for example, the Brown curve prefers equal masses more than our result here. However, these in-spiral merger ring down waveforms assume a quasi-circular binary, and some studies have suggested that this might be an eccentric binary, and there's of course some uncertainty. There might be some biases, systematic biases in these waveforms, which become more apparent as the ring down is the relatively loud part of this signal, whereas the in-spiral merger have less signal to noise ratio. So there is this tension that is interesting at this point. And finally, the third analysis that we can do with this is essentially the second analysis again. That is, we impose the relation between the different modes parameters as predicted for a perturbed Kerr black hole. But then we allow for a fractional deviation in the frequency and in the damping time of the second mode. And the expectation for these two parameters from general relativity is, of course, that the values for both is 0. And the previous studies that we made suggested that the level we're interested in to test these deviations is to constrain them to less than 20%. And this we expected to be possible only with future detector designs on reasonable timescales. However, for this event, we actually find that we can constrain the deviation in frequency to be less than 12% from the predicted value for general relativity. So this is a rather surprisingly well-constrained deviation. And you can see that the median value is an offset of about 1%, practically at 0 here. The damping time is generally less well measured, and such constraints are thus weaker, but the deviation in frequency is constrained very well. So surprisingly, we find that we can do black hole spectroscopy with advanced LIGO. And we find that this event, 190521, contains a loud measurable 3-3 ring down mode from the quasi-normal mode spectrum. And if this was a quasi-circular binary, then the initial black holes must have had unequal masses, and the remnant object is very well consistent with a Kerr black hole, constraining the deviations in the frequency prediction to within 12% of this prediction. And with this, thank you for your time.
Thank you very much for excellent talk. We have time for a couple of questions. If there are no other questions, I would like to ask you my question. So you, in your talk, you mentioned that it's not reasonable to expect to find charged astrophysical black holes. I completely agree with this claim. But meanwhile, people suggested many ways to get Reissner-Nordström metric, for instance, in Randall syndrome theories like tidal charge, and also like charge may rise due to scalar tensor theories like Hardetsky and other theory. In principle, you could introduce charge as additional parameter in your consideration. I think it's not a big deal, it's not a big problem, but in this case, it's also maybe some, let us say, indication of, let us say, deviation from general relativity or not. Thank you.
I do not know what exact effect the charge would have on the spectrum of quasi-normal modes you would expect.
No, it may be charged black hole due to tidal charge, due to extra dimension, like Randall-Sundrum found. So not Randall-Sundrum, Dadich et al. Found that if there is a theory with extra dimension, in this case, one of solution of this theory is Reissner-Nordstrom, but it's not electric charge. They call it like tidal charge. But in principle, we have, so at the first glance, we have no constraint on, let us say, tidal charge, because we don't know, but electric charge is, of course, should be very small. But this, let us say, extra parameter with, and people are considering and speculating about value of this, let us say, constraint on this tidal charge from different, let us say, observational data. It may be, I mean, it may be significant. So it's simply like speculation. Since you consider some deviation from general relativity, again, let us say versions of Hardetsky theory, also sometimes they have solution like with Q parameter, like Reissner-Nordstrom. But again, it's not electric charge. In this case, let us say at the first glance, no significant constraint on this parameter. But this, let us say, consideration of, let us say, quasi-normal modes, etc. So in principle, you could, let us say, constrain this parameter from this data. It seems to me. I'm not sure, but you're expert. Thank you.
Well, yes, I agree that if there is a prediction that you can make for the quasi-normal modes that you would expect for this alternative model, and if there is indeed a deviation between that and the Kerr prediction, then yes, then for this event, for example, at least we could say that it has to be less than these 12% that we measured. So the interesting question is, I think, which theories predict how much of a deviation in this frequency spectrum.
Yes, yes, exactly. Thank you very much. But we have still time for 1-2 short questions. Valeria, do you want to ask a question? Because your microphone is on.
No, sorry, I just came in the session. Sorry.
It's fine. In this case, so let us thank all speakers, because for their perfect presentations and perfect timing. So we finished on time as it was requested. Thank you very much. Bye.